Binomial expressions. An algebraic expression having two terms is called binomial expression. If the algebraic expression having three terms instead of two, then it is called trinomial expression. Now we are going to learn about binomial expression. So let's look what we have done earlier. We are very much familiar with these expressions. Similarly, now I am going to explain what is a binomial expression. This is our binomial expression with the index 3. This is our term 1. This is term 2. This is term 3 and term 4. Now we have the expanded form of a binomial expression. Expansion of a binomial expression for n that belongs to natural number is called binomial theorem. Again, expansion of a binomial expression for any natural number is called binomial theorem. Let's talk about the observations on these expansions. So we have binomial expression in this example with expanded form. Observations: 1. Total number of terms is 1 more than the index. As our index is 3 and number of terms is, I think it's 4. Total number of terms is 1 more than the index. Second, in all the expansions, it is clearly visible that power of A goes on decreasing. See, here we have 3, here we have 2, here is 1 and no A at all. And the power of B goes on increasing. No B at all, B power 1, B power 2, B power 3. So, power of A goes on decreasing by 1 and the power of B goes on increasing by 1 in successive terms. The sum of indices of A and B in each term is equal to the index of A and B. Sum of indices of A and B in each term. So we will look for the sum of indices in the expansion of a binomial expression. In term first, we have only A having index 3. So index is 3. No need to add because there is no B here. Sum of the indices of A and B in the term 2 is 3. In term 3, again the sum of the indices of A and B is 3. In term 4, index is 3. In each term, we have sum of indices equal, that is 3, that is equal to the index of A plus B. And what is that? What is the index of A plus B? 3. 3 is equal to these 3. Hence, the sum of indices of A and B in each term is equal to the index of A plus B. In earlier expansions of binomial expressions, we have seen examples and we are doing this for very long. For example, x plus y square is equal to x square plus 2xy plus y square. Binomial expression. This is the expansion Now it's time for writing coefficients. Coefficients for index 2. At first term, we have coefficient 1 here. So I will write 1. At the second term, we have coefficient 2. So I will write 2. And at the third term, we have again coefficient 1. So again, I will write 1. If I add these two numbers, 2 plus 1, 3, 2 plus 1, 3, and starting and the ending of the coefficients with 1. Now you got the coefficients for the next index. Here it is. Writing the coefficients. For example, in this binomial expansion, at the first term, we have coefficient 1. At the second term, we have coefficient 3. At the third term, we have again coefficient 3. And at the fourth and last term, we have coefficient 1. Hence, by adding them together, these coefficients together, we get the next row of coefficients for next index. In this case, this is the row of coefficients for the index 3. This is the Pascal's triangle with the coefficients and index. It looks like triangle. At the top, for index 0, it has coefficient 1. At each row, coefficient starts with 1 and ends with 1. Starts with 1, ends with 1. Earlier I told that how these two numbers by adding together give this number for the next row, and the process goes on till any index of our interest. Now it's easy for writing any expansion for any binomial expression by using the Pascal triangle. For example, if I want to expand binomial expression x plus y index 5 by using Pascal's triangle, now we have row 5th here in the Pascal's triangle. I will use this and simply write the equation in a very easy way. You also can do this. As you know, the power of x decreases as goes on, while the power of y increases as goes on. And leave the spaces for the coefficients. Now I am using the row of index 5 for the coefficients. Here starting with 1, and then what do we have? 5, I will write 5. Then 10, I will write 10. Then again 10, I will write 10. Then 5, I will write 5, and then 1, then 1. That's how we use Pascal's triangle to write the coefficients. But it's easy when we know the rows, or we can easily get the rows. What if I have to expand x plus y 17? We have to get to the row to write the expansion, and then for this we have to write all the rows, and that will be a very hectic process. So what shall we do? We change the method with a simple one. Let's see. For this, we make use the concept of combinations to rewrite the numbers in the Pascal's triangle. And how did we do it? Let's see. We know that number of combinations of n different things taken r at a time is given by n factorial, r factorial, n minus r factorial, where r is greater than or equal to 0 and less than or equal to n. We are going to use this term in the Pascal's triangle, where n is a non-negative integer, n C r for index 0. The index number will be the same, but r changes. R for the index 2 starting from 0 goes on till being 2, and the rows go on. We know that beginning of the coefficients and ending of the coefficients, beginning, ending, always is 1. Previously, I have shown you how to write the coefficients in the expansions. Now we are going to use coefficients with the NCR. Observing this pattern, now we can write row of Pascal's triangle for any index without writing earlier rows. How? Let's see. If I write binomial expression x plus y, index is 8, again decreasing of x and increasing of y. First I will write this. Now we write the coefficients for the expansion. Index is 8, c, and r is 0. 8, c1, 8, c2, c5. Using this row, an expansion of a binomial to any positive integral index, say n, can now be visualized using these observations. And now we are in position to write the expansion of a binomial to any positive integral index.